Welcome to Dart Tutors. Today we will explore Chapter 27 of the IB Mathematics Analysis and Approaches Higher Level Curriculum, Discrete Random Variables. In this video, you will learn the fundamental concepts of probability distributions for discrete random variables, a key topic in statistics and probability. By the end of this session, you will be able to define discrete random variables, construct probability distributions from various scenarios, and determine if a given function is a valid probability mass function. Let's begin. We often encounter variables in the world that depend on chance events. For example, the number of goals in a football game or the sum when rolling 3 dice. Because of this random element, we cannot predict the exact value these variables will take. To describe these situations, we use what are called random variables. A random variable, which we typically denote with a capital letter like X, is a numerical description of the outcome of a random experiment. This means it assigns a number to each possible outcome of an experiment. Random variables are categorized into 2 types, discrete and continuous. A discrete random variable, our main focus in this chapter, can only take a finite or countably infinite number of specific, distinct values. You determine its value by counting. Examples include the number of heads when tossing coins or the number of defective items in a batch. In contrast, a continuous random variable can take any value within a given range on the number line. You determine its value by measuring. Examples include a person's height, the volume of water in a tank, or the time it takes to complete a task. Let's work through an example to solidify this concept. Suppose a supermarket has 3 checkouts, A, B, and C. An inspector checks the weighing scales for accuracy at each checkout. We define our random variable X as the number of accurate weighing scales. Our task is to list the possible outcomes and the corresponding values of X. Let's use a table to visualize this. We'll denote an accurate scale with a check mark and an inaccurate scale with an X. First, we list all the possible outcomes for the 3 checkouts, A, B, and C. There are 2 to the power of 3, or 8, possible combinations. For each outcome, we count the number of check marks to find the value of our random variable, X. For example, if all scales are inaccurate, X, 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 then X is 0. Looking at the table, we can see that the distinct possible values for X are 0, 1, 2, and 3. This confirms that X is a discrete random variable, as it takes on a finite set of specific values. Now, let's explore a more complex scenario. Suppose we have a bag containing 4 red and 2 blue marbles. We select 2 marbles randomly without replacement. Let X denote the number of red marbles selected. The first step is to state the possible values for X. Since we are selecting 2 marbles, we can have 0, 1, or 2 red marbles. So the possible values for X are 0, 1, 2 values. The next step is to find the probability of each of these outcomes. A tree diagram is an excellent tool for visualizing this process. On the first selection, the probability of picking a red marble is 4 out of 6, and a blue marble is 2 out of 6. Because the selection is without replacement, the probabilities for the second draw change. For example, if we picked a red marble first, there are only 3 red marbles left out of a total of 5. So the probability of picking another red is 3 out of 5. The complete tree diagram shows all the paths. We can see 4 possible outcomes: red-red, red-blue, blue-red, and blue-blue. Each corresponds to a specific value of X. Now let's calculate the probability for each value of X. For X equals 2, the outcome is red-red. We multiply the probabilities along the path. So the probability of selecting 2 red marbles is 4, 6 times 3, 5, which equals 12, 30. The value of X for this outcome is 2. Next, let's find the probability for X equals 1. This can happen in 2 ways: red then blue, or blue then red. We calculate the probability of each path and add them together. PRB is 4, 6 times 2, 5, which is 830. PBR is 2, 6 times 4, 5, also 830. Their sum is 1630. So, the probability of selecting exactly 1 red marble is 1630. Finally, for X equals 0, the outcome is blue-blue. The probability of picking 2 blue marbles is 2, 6 times 1, 5, which gives us 230. We can now construct the probability distribution table for x. To verify this is a valid distribution, we must check two rules. First, all probabilities are between 0 and 1, which they are. Second, the sum of all probabilities must equal 1. This confirms our distribution is valid. We have successfully constructed a probability distribution for a discrete random variable. Let's summarize the key properties of a discrete probability distribution. For any discrete probability distribution, two conditions must always be met. First, every individual probability p of x equals x sub I must be between 0 and 1. A probability cannot be negative, nor can it be greater than 1. Second, the sum of all the probabilities for every possible outcome must equal 1. This ensures that we have accounted for all potential results of the random experiment. In summation notation, this is written as the sum of all p sub I equals 1. We can represent these distributions in a few ways. A table is useful, but a graph, specifically a bar chart, provides a visual representation. The height of each bar corresponds to the probability of that outcome, and the sum of the heights of all bars is 1. Let's apply these properties. Consider the probability distribution shown in this table. Our task is to find the value of k that makes this a valid probability distribution. The values for x are 0, 1, 2, and 3. The corresponding probabilities are k2, k3, k, and k. We must use the second property of probability distributions. The sum of all probabilities must be equal to 1. So we set up the equation. K plus 2k plus 3k plus dk equals 1. Combining the terms, we get 7k equals 1. Dividing by 7, we find that k must be 1/7. This gives us a specific value for k. Let's check the first property. 0 is less than or equal to p sub I, which is less than or equal to 1. The probabilities are 1/7, 2/7, 3/7, and 1/7. All of these are between 0 and 1, so the distribution is valid. A special type of discrete distribution is the uniform distribution. A discrete random variable x is called a uniform discrete random variable if every one of its possible values has the exact same probability of occurring. The classic example of this is a fair six-sided die. The possible outcomes are 1, 2, 3, 4, 5, and 6. Each number has a probability of 1/6. Since all outcomes have the same probability, rolling a single die is a uniform discrete random variable. By contrast, rolling two dice and taking the sum is not a uniform distribution. The possible sums range from 2 to 12. However, some sums are much more likely than others. A sum of 7, for instance, has a probability of 6 out of 36, which is 1/6. A sum of 2, on the other hand, has a probability of only 1 out of 36. Since the probabilities are not all equal, the sum is not uniformly distributed. Beyond just listing probabilities, we can also define them using a probability mass function, or PMF. A probability mass function is a function, often written as p of x or p of x equals x, that describes the probability distribution of a discrete random variable. The input, x, is one of the possible values the random variable can take, and the output, p of x, is the probability that the random variable x takes on that specific value. To be a valid PMF, a function must satisfy the same two properties we discussed earlier. The probability for any value must be non-negative, and the sum of all probabilities over the entire domain must equal 1. Let's look at an example. We are given the function p of x equals the quantity x squared plus 1 divided by 34 for x equals 1, 2, 3, and 4. We need to show that this is a valid PMF. First, we calculate the probability for each value of x. For x equals 1, p of 1 is 2/34. For x equals 2, p of 2 is 5/34. For x equals 3, p of 3 is 10/34. And for x equals 4, p of 4 is 17/34. We check the first property. Are all these probabilities between 0 and 1? Yes, they are. They are all positive and less than 1. Now we check the second property. Does the sum of all probabilities equal 1? We sum the probabilities. 234 plus 534 plus 1034 plus 1734. The total is 3434, which is 1. Since both properties are satisfied, we can conclude that this function p of x is a valid probability mass function. It accurately describes a discrete probability distribution. Now, let's work backwards. If we know a function is a PMF, but it contains an unknown constant, we can find that constant. This is a common IB-style question. Consider the function p of x equals k times the quantity x plus 2 for x equals 1, 2, and 3. We are told this is a probability mass function, and we need to find the value of the constant k. As before, the key is the property that the sum of all probabilities must equal 1. First, let's write out the probabilities for each value of x in terms of k. P of 1 is k times 1 plus 2, which is 3k. P of 2 is k times 2 plus 2, which is 4k. And P of 3 is k times 3 plus 2, which is 5k. Next, we set up our equation. The sum of these probabilities must be 1. Combining the terms, we get 12k equals 1. Dividing both sides by 12, we find that k must be 1 to 12. Let's check our answer. The probabilities are 312, 412, and 512. All are positive and less than 1. Their sum is 1212, which is 1. So our value of k is correct. So far, we've dealt with finite discrete variables. However, some random variables can take on an infinite number of values. This often leads to using geometric series. Here is an IB-style problem involving an infinite number of values. A discrete random variable x has the probability mass function p of x equals a times 2, 5 to the power of x, for x equals 0, 1, 2, and so on. We need to find the value of a. The principle remains the same. The sum of all probabilities must equal 1. The difference is that this sum is an infinite series. Let's write out the sum. We need to find the sum from x equals 0 to infinity of a times 2 to 5 to the power of x, and this sum must be equal to 1. We can factor out the constant a. We are left with the infinite geometric series, 1 plus 2, 5 plus 2, 5 squared, and so on. The formula for the sum of an infinite geometric series is a over 1 minus r, where a is the first term and r is the common ratio. In our series, the first term is 1, and the ratio r is 2, 5. Substituting these values, we get 1 over 1 minus 2 to 5, which simplifies to 1 over 3, 5, which is 5, 3. So our equation becomes a times 5, 3 equals 1. Solving for a, we find that a must be 3, 5. This ensures that the total probability adds up to 1. Now that we know how to define and create probability distributions, let's explore some key characteristics. We've already seen how to visualize a distribution using a bar chart. Now we'll look at two numerical descriptors, the mode and the median. The mode of a discrete probability distribution is the outcome, or value, of the random variable that has the highest probability. Looking at a bar chart, it would be the x value of the tallest bar. The median is the outcome at the 50th percentile. It's the first value of x for which the cumulative probability is at least 0.5. To find it, you list the outcomes in order, sum the probabilities, and find the first outcome that crosses the 0.5 threshold. Let's find the mode and median for the marble selection example we did earlier. Here is our probability table. To find the mode, we look for the highest probability. The probabilities are 230, 1630, and 1230. The highest probability is 1630, which corresponds to x equals 1. So, the mode of this distribution is 1. The most likely number of red marbles we will select is 1. To find the median, we calculate the cumulative probabilities. We start from the smallest x value. For x equals 0, the cumulative probability is p of x less than or equal to 0, which is just p of x equals 0 or 230. This is 0.67, which is not yet 0. Next, we add the probability for x equals 1. The cumulative probability for x equals 1 is p of x less than or equal to 1, which is 2 to 30 plus 1630, or 1830. 1830 simplifies to 3.5, or 0.6. This value is greater than 0.5. Since x equals 1 is the first outcome where the cumulative probability exceeds 0.5, the median of the distribution is 1. The median and mode happen to be the same in this case. We've covered the core concepts of discrete random variables, including how to define them, construct their probability distributions, and find the mode and median. Now, let's test your understanding with some practice questions. Pause the video and try to solve these yourself before you see the solutions. This is an excellent way to prepare for the IB exam. Here are your 5 practice questions. They cover the types of problems we've discussed today. Take your time to work through them. Welcome back. Let's go through the solutions. Remember, the process is as important as the final answer. Question 1 asked you to classify the random variable, the number of defects in a manufacturing process. The number of defects is obtained by counting 0 defects, 1 defect, 2 defects, and so on. Since it can only take distinct countable values, it is a discrete random variable. Question 2 asked you to construct the probability distribution for the number of heads, x, in 2 coin tosses. First, the possible values for x are 0, 1, or 2 heads. The total possible outcomes are HH, HT, TH, and TT. One outcome has 0 heads, TT, 2 have 1 head, HT, TH, and 1 has 2 heads, HH. Therefore, the probabilities are 1/4 for 0 heads, 2/4 or hi-hat for 1 head, and 1/4 for 2 heads. Question 3 asked you to find k for a given distribution. Using the rule that the probabilities must sum to 1, we add the given probabilities. 0.2 plus k plus 0.4 plus 0.1 equals 1. This simplifies to 0.7 plus k equals 1. Therefore, k must be 0.3. Question 4 asked you to show P il x10 for x equal 1, 2, 3, 4 is a valid PMF. We find the probabilities for each x. They are 1 to 10, 2 to 10, 3 to 10, and 4 to 10. All are between 0 and 1. Their sum is 1 plus 10 to 10, plus 2 to 10, plus 3 to 10, plus 4 to 10, which equals 10, 10, or 1. Both conditions are met, so it is a valid PMF. Finally, Question 5 asked for the mode and median of a distribution. For the mode, we look at the probabilities. The highest probability is 0.4, which corresponds to x equals 1. So the mode is 1. For the median, we find the cumulative probabilities. X less than or equal to 0 is 0.1. X less than or equal to 1 is 0.1 plus 0.4, which is 0.5. Since 0.5 is the first value to reach or exceed 0.5, the median is 1. I hope you did well on these questions. We have now covered how to define discrete random variables, construct probability distributions, and identify valid probability mass functions. This provides a strong foundation for the remaining topics in this chapter. Thank you for joining me on Dart Tutors. This concludes our video. For more IB mathematics resources, visit darttutors.com. We offer online and in-home tuition to support your learning journey. Thank you for watching.